This video will show you the impact online rework has on your ability to deliver product. You'll see how you can reduce your lead time and get more customers. So here I used FlexSim for modeling a manufacturing line. This program has been tested against an actual line. It had different first pass yields, different cycle times, but it was accurate within about 5% of the numbers that you're going to see at the end. It's important to note that this is just a simulation. I have programmed the model to act a certain way. It will act the way I ask it, unlike personnel who may be under a deadline. Personnel on lines may give special treatment to some products and even set up spare equipment to reduce the turn time. We don't really want this. What we want is a line to run in a way that no special considerations, no additional resources are needed, just that the line runs in an easy and logical way and we know what we're going to get without the need for any deviations from normal running, which eat up your resources in engineering and line leads and technicians. So what I'm saying is if your lines ran without disrupting the normal process and taking up more resources, this is what you would have for your turn time. Now, this little dot up here with all the red lines on it, that's a 288 fiber cable, and it's already gone through assembly. It's going to go through assembly to then a value added activity. When I want you're going to run it now for this first inspection point. You know what? I'm going to slow this down a little bit more. Let's run that again. So let's see if we can slow this down just a little bit more. Okay, now maybe it'll make more sense. See, now it comes into value added activity, comes into an inspection point, has to wait to get reinserted, has to wait again. Finally, it gets through that inspection point. All 288 are good, goes through the second inspection point, has to wait to be reinserted. And when it comes back up here, a certain number of those fail because there's 90% yield here. So you get the idea. Now we're going to go to a much simpler model for you to understand. So I put this model together because it's going to be much easier to see the impact. You're not going to see everything, but you're going to get the idea. Rework loops piecemeal your rework, and reinserting product on a line costs you time in the form of non-working WIP, as well as taking up a lot of space in your inventory. So let's pull up this model, and it'll be much easier for you to see how this is working. So this is our model. And this is a high complexity product where there are 288 base process units or connectors that make one product. We're going to be looking for how many workstations it passes through, the number of connectors passing through the bottleneck, and the number of times the product gets reinserted into the line. So right now, there are 11 workstations on the line, and the product has passed through 3 workstations so far. So we're going to begin counting the number of connectors that go through this workstation with a red highlight on it, because that is the bottleneck. That's the bottleneck according to the workstation factor in your enhanced value stream map, which is what you should be using. So keep an eye on the pass-through workstations and reinsertions, as these 2 items contribute to lengthening your turn time. So at a 90% first pass yield, 28 connectors are sent back to polish at end. There's some rounding going on here, so you'd think maybe it's going to be 29, but it's actually 28. But don't worry, the later numbers will make more sense. So what you're not seeing here are the other products on the line. I removed them to make it easier to see. FlexSim simulation does show these. That's what makes it so difficult to watch, and it's so small. But I'll show you the numbers from FlexSim, which are pretty accurate. So we add 28 connectors to the bottleneck and one insertion back into the line. And now 3 of those 28 go back again. You see what's going on here? We're kind of piecemealing our rework. We're constantly sending non-conforming product back immediately. This means we're putting the product in non-working whip constantly, which kills our turn time, which is the portion of your lead time that manufacturing takes. So add 3 more connectors to the bottleneck, and then we've got 2 insertions onto the line. But now all 288 connectors can go to form. So we add 25 connectors through the bottleneck. We've got 3 insertions on the line. Of those 25 sent back from form, 3 have now filled it in because of a 90% first pass yield. This contributes to inflated non-working whip, more product in the way of production, more complex processes for reworking, and more turn time. We're going to speed this up now so you have an idea of what's going on. Keep an eye on the number of pass-through workstations, and then also keep an eye on the connectors going through the bottleneck. There's 4 insertions in the line, 5 insertions, 6 insertions, 7 insertions. Notice how now a few of those that failed at ILRL are failing at end. We've got 8 insertions, and a few more fail because of 90% yield. I've got 9 insertions. And then at form we get a few failures, so we have 10 insertions. And we just keep going and going. There's 11 insertions so far. 12. 13. And remember, what you're not seeing are all the other products on the line that extend that time it takes to get reinserted. That's 14 reinsertions. And 15. 16. 17 reinsertions, and 445 connectors have gone through that bottleneck. And there's 18 insertions, 446. Now, you think this might be the end? Let's send 19 insertions, 449 connectors. No, we still got one. So that's 20 insertions, 450 connectors so far. So we have 450 connectors being processed in your bottleneck to get 288 good connectors to make one product. That product passed through 87 workstations instead of 11. That's almost 8 times more than what's needed. The product was reinserted into the line 20 times. Every time that product is reinserted, it means the product was sitting in a non-working whip, waiting to be worked on, getting in the way of manufacturing, causing manufacturing to manage the large number of units waiting for reinsertion. According to FlexSim, at times there are 9 products waiting. Some of those products can be worked on in parallel, but that's still a minimum 5. This kills your turn time. And now we're going to go back. So let's look at the results. The product passed through 87 workstations instead of 11, which would have required 100% roll throughput yield to go through 11, which is the perfect labor, which is 21 hours if the roll throughput yield was 100%. And we can use that to compare against the other times because that's what we want to do. We always want to compare ourselves to perfection. So the added labor for online rework is 30.3 hours or 144% more labor because of our roll throughput yield. and because of the way that we're dealing with our rework. The portion of lead time attributed to manufacturing is what I call turn time. Here, turn time for online rework is 231 hours. For 2 shifts, working 15 hours, having 15 hours of working time per day, that would be 15.4 days to deliver this product. After that, you get another product off the line about every 8 hours. So we have 14 operators on the line as of now. The line's output is 685 connectors per day because of the rework loops and roll throughput yield. OCE is 23%, which is expected for any manufacturing area that has not been through the enhanced value stream map or some sort of process improvement. Goals should be around 70 to 80. We're going to go in more detail on OCE in the next video, but the bottleneck passed 450 connectors through to get 288 good connectors for one product. That to me seems a little bit crazy. So we're going to review a model that shows you offline rework, and you're not going to be seeing everything, but you're going to get the idea again. There's going to be other product on the line, so the times for reinsertions and all that, turn time is going to be calculated using FlexSim, but I'm just going to show you how it works here. So here we decided to add uh, a fix and polish between signal and packaging. You see them below, and this added 2 operators to make 16. So about half the connectors will need to be reworked at polish and half at a fix. Unlike earlier in the line, uh, we can do both later on because there are already some of them that are just need to be repolished. So fix and polish are 2 workstations all rework came back to, but instead of reinserting the non-conforming product, we just put all product through these areas. Since this is a high complexity product, we took the roll throughput yield to the power of the number of connectors to see what the rework free probability is. The RFP, or rework free probability, is the probability the product will not need rework, and it's basically 0. I'm going to let this run for a bit to save time. Pay attention to the connectors through the bottleneck and pass-through workstations. We're also going to look at reinsertions. Notice that each inspection point is only processing the passing connectors from the previous inspection point, and so the time it takes to process the product gets less. Putting the product back through these areas will mean they will have a higher efficiency. Just wait for the results in the next slides to see the impact on turn time, output, and OCE. So there's one insertion. Once reworked, we do reinsert on the line because all the workstations after polish can handle doing the extra rework without becoming the bottleneck. Two insertions. Remember we had 20 before. 3 insertions. 4 insertions. See the number of connectors? We're down to only 1 connector needing to be processed. Do you notice the total number of connectors passing through the bottleneck is the same online as it is offline? But we have 2 workstations instead of 1. If you notice, there's 2 red workstations. The polish workstation in position 5, up above, the original one, is putting product out at a much faster rate because they're only doing brand new connectors. The second polish station, which is processing 166 connectors for every 288 the other one does, so they don't have any issues keeping up. But the line is producing at the lower workstation factor, so our output is higher. You'll see that in a moment. There's 5 insertions. So we passed through 41 workstations, 5 reinsertions, and now we're going to review the rest of the data from the FlexSim simulation. So here you can see the impact of online rework loops versus a recovery area. In this case, the recovery workstation reduced the pass-through workstations to 47% of what online would have been. The perfect time in the first column or in the first row is still 21 hours. There's no change there. The added labor is 27.4 hours instead of 30.3, which is 90% of what it was before for online. This is because we're not piecemealing the rework and we're accumulating the non-conforming connectors and working them in parallel at points and reducing the labor in that way. This also reduces the pass-through workstations, which has a positive impact on added labor, but the highest impact is on turn time. The portion of lead time attributed to manufacturing is what I call turn time. Here, turn time reduces from 231 hours to 51 hours. It's 22% of what online rework is. So to get this, we added 2 workstations and 2 personnel for a 14% increase in labor. But this 14% increase resulted in an increase in output of 158%, or from 685 connectors per day to 1,080. I'd take that any day of the year. This is because the first bottleneck is doing nothing but producing product at the fastest rate possible, while the second bottleneck workstation in the rework area is processing 166 connectors for that first bottleneck's 288. As far as the decision on if you add workstations to a line or convert one line to support more than one line, it's not always clear. When you convert a line to a recovery area, uh, this area will be fewer in personnel, as it only has to deal with the workstations involved in the rework loops. The original areas will probably be reduced as well because anything after that, like packaging, could be combined as well. So this recovery area will support many lines depending on your roll throughput yield. Basically though, the higher the roll throughput yield, the more lines the recovery area can support. In another case, like this one here, you may find it best to add workstations to the end of the line. In this particular case, it was best to add 2 workstations on the end of the line. Basically, actually not quite the end of the line, but right before packaging. Now, this resulted in the line increasing its output. Creating a recovery area will always decrease your turn time, increase your output, and increase OCE. Here, we went from an OCE of 23% to 34%, resulting in a 142% increase by increasing the performance portion of the OCE equation. Next video is going to talk in more detail about OCE and OEE, but to decide on what recovery area is best, look at first pass yield, workstation factors, the number of workstations having less than 100% first pass yield, and where these workstations send non-conforming product. Generally, roll throughput yields above 78%, you can take one line of 3 and convert it to support the other 2. Below 78% roll throughput yield, you may want to review adding workstations. When roll throughput yield is above 90%, you're going to need a lot more lines. It's 8 to 20, depending on what your roll throughput yield is. But the cost benefit analysis that you will do will show you it's always better to have a recovery area. When you're deciding what kind of recovery area to use, it's easy to get lost in analysis paralysis. Sometimes it can be very hard to predict the impact accurately. So if you get stuck, or maybe I should say when, because you probably will get stuck at some point, stuck on what to do, you always go back to your project charter. Take the data as far as you can and implement something with a control chart in place. If you did the define, measure, and analyze phases according to the control and using the control phase tools, you should see the change in turn time and output quickly and learn what reality is. So don't forget, a decision you can learn from today is better than one never made. Don't be afraid to try something out. Just make sure you have a control chart in place so you know as quickly as possible if you're getting the results you desire. So here are some formulas that you may find useful if you plan to do some calculations in Excel. So to calculate the percentage of added connectors going through the bottleneck or workstation, you can take 1 divided by the roll throughput yield minus 1. That gives you, here we got a roll throughput yield of 80%, 25%. So you're going to get 25% more connectors through the bottleneck. Now the enhanced value stream map does this calculation for you, so you can see it there really easily. Um, for the number of lines a recovery area can support, basically you just take 100 divided by whatever the result was from up above, that's 25. So that's 4. So that means that 5 lines are needed to convert 1 to a recovery area. You can support 4 lines with 1. But you always round down to the nearest whole number. So if you had 4.5, just say 4. Even if you had 4.8, say 4, round down. If you have less than 2 as a result here, then you might want to add workstations. You might consider adding workstations anyway, even if you can support with 1 line. Just do the calculations. So to calculate the number of rework loops, you take the natural log of 1 divided by the connector count, and you divide that by the natural log of 1 minus first pass yield. And that's going to tell you the number of rework loops that you're going to experience. Here, you always round up to the next or the nearest whole number. These formulas are in the enhanced value stream map. They're used in different ways. You can see them, but I'm just providing them here in case you want to do your own calculations. So in conclusion, to turn the lights on in your hidden factory, look for how your team acts in non-conforming product. Rework is often the biggest hidden factory in manufacturing. You can calculate the added labor and time, but until you map out reality, you never really know the cost of quality. Looking closely at the way you deal with non-conforming product will turn the lights on in this common hidden factory. Next week, we'll talk about OEE and OCE. What are they and which ones should you use? If you found the video useful, like it, subscribe to the channel, and share it with anyone else who may find it useful. If you didn't find this video useful, then subscribe in the hope that an upcoming video will be. Eventually, we're going to go through projects using Lean Sigma, Six Sigma, as well as the tools needed to support them. Remember, it's better to learn from a mistake than to do nothing. Until the next video, keep your data clean and take care.